I'm going to focus primarily on Okanagan Lake. And again, all of this information comes from the Okanagan Water Supply and Demand Study that was coordinated by the Stewardship Council. There's a cartoon of the basin with all of the sort of major hydrologic components shown there. We have an annual precipitation, varies from about 300 millimeters on the valley floor up to 1,000 millimeters in the higher elevations of the subalpine, with a basin average of about 650 millimeters. And as we see in this particular cartoon, we get our weather from the west. Precipitation largely comes from the south and the southwest, and at higher elevation, precipitation falls as snow. And as snow generates about 75%, snow melt generates about 75% of the total runoff into the basin. But the key factor here is that although we get on an average of 650 millimeters of precip every year, 80% of that water is returned to the atmosphere through evapotranspiration. So only 20% of the precip that falls enters into or stays in the hydrology of the basin. And a challenge for the council was to come up with good estimates of these evaporation rates. In particular, the evaporation that occurs from the lake itself, and depending on the year and the conditions, we lose from the lake surface 50 to 75 centimeters of water. So up to a meter of water evaporates off the lake every summer. Tremendous amount of water when you start calculating it in terms of cubic meters of water. The lake, though, is huge, right? 25 cubic kilometers of water is stored in the lake, and the water has a mean residence time of 60 years. So I guess in lake terms, that's a very, very slow turnover, and leads to this sort of what we sometimes refer to as the illusion of abundance of water here. Although we've got this tremendous volume of water that's sitting there for a long period of time, the in and the out is relatively minor compared to the total volume in there. Another component of the cycle is groundwater here, and has been a challenge to understand what happens with that part of the snowmelt that doesn't immediately run off over the surface but enters into the ground. Most of it, well, I'll get into a little more detail later. Most of it does end up in surface stream flow at some point, but a small amount of it does work its way through the groundwater system and into the lake, and we get about 2 to 4 million cubic meters of groundwater feeding the lake. But to put it into perspective, that's only about 1% of the amount that's lost through surface evaporation. And the outflow volume of the lake is about double that lost by evaporation. So we lose water through evaporation and through outflow down through the lake. In terms of our water users, most of our water comes from surface sources, and the network of water purveyor systems that we have here in the valley. Most of it coming from surface sources, and about a quarter of it from groundwater. The imported water is really diverted water into the basin here, and there's a few locations where that occurs. In terms of who's using the water, the biggest user of water in the Okanagan Basin is agriculture, and water that's used for irrigation. And second to that would be the domestic outdoor use, and that's a kind of fancy way of saying, the water we use to irrigate our lawns and to fill our swimming pools and this sort of thing. The outdoor use component is very large. Golf courses, about 5% of the water, total water use is by golf courses. And then the domestic indoor, which is less. So this outdoor use, this is the summer use. The peak flows and water use that we see is really a result of this. The domestic indoor, of course, is fairly consistent through the year. And then relative to that, the industrial and commercial uses is actually quite small compared to our domestic use. So the complexity of Okanagan water management. The basin is experiencing a variety of pressures on its water resources, and it has the highest ratio of population to water supply of any basin in Canada. So kind of the reverse to that is the least amount of water available per person in the country. So we're really limited. Water is a limited resource. And then compounding that is this myriad of water suppliers, over 100 of them, I think, in the basin, 4,000 active water licenses issued by the province. So it's not a single entity that's managed by one sort of overseer. And in fact, it's this situation. This situation that led probably to the Okanagan Water Basin board being formed and trying to somehow coordinate all of these different groups. Population growth, changing climate, and increased water demand continues while water supply may decrease. And to this extent, land use planning is really a key here in terms of managing this demand in the future. There's not a whole lot we can do in terms of land use planning in the supply side, but on the demand side. So here's some modeling work that was done by Denise Nielsen's group, and it looks at the impact on water of constrained footprint to urban growth versus what we're calling sprawl here. But what we really mean is where we allow development to spread out onto parts of the landscape that currently we don't water. So we're not talking about converting orchards into urban land. We're talking about the creep of urban land up onto the grassland slopes and the hillsides and those areas where we're not currently conducting agriculture. If we sprawl out onto those, then we essentially are now needing water in parts of the landscape where we didn't need water before. And if we are building houses with nice big backyards and everybody, of course, wants to water that backyard, that's the kind of trend that we would see, is this increase in water consumption. And this is being modeled against projected climate conditions and projected changes in that potential evapotranspiration as we move forward. So keep that in mind, that the decisions you make in the land use planning realm have long-term implications potentially to our water supply and demand conditions here in the valley. Other big one is that the ratio, and again, kind of looking ahead here, the ratio of snow to rain is going to change. We get, on our uplands, we get pretty much snow in the winter at higher elevations, and we see that this is going to change. We'll get more rain, and that has implications for infrastructure design and management. So this is on the supply side now, the challenge on the supply side. And but there is significant variation, as we saw in some of those earlier graphs, year to year in terms of our inputs, and this can generate both water shortages and floods from one year to the next. So this chart here shows you the inflow into Okanagan Lake over the last 75 years, 80 years or so, and you can see that the variation in these bars. We have some years with tremendous inflow and other years with very limited. 2003 is right there. You can see the inflow that year. The all-time driest periods we've had in the historical record were for a 3-year period, 1929 to 1931. Our lowest inflows to the lake were recorded. So this is our historical drought, and we use the flow regime as best that we can recreate it from that period of time to really understand what a real drought, a prolonged drought, would look like in the valley here. So I'll come back to this a little bit later on when we talk about drought, but just to give you an idea of the variation in flow into the net flow into the lake from year to year. The other challenge, of course, is that our water supply arrives between April and June as the snowpack melts. But this timing's not the same as the water demand, which is highest during the summer months. So we're always having to deal with this issue of storage, how to store water. And in some ways, we use the lake as the biggest reservoir we've got. And for those purveyors that extract water out of the lake is there and doing that function. But we also have many small reservoirs on the upland here. Basically every major creek feeding into the Okanagan Lake in the RDOS has some sort of storage or containment structures on it. This is a list of all of those that occur. This is just Okanagan Lake tributaries within the RDOS boundaries. So it wouldn't include Oliver and Soyuz and down there. But Eneas Creek, Trout Creek, a whole bunch of reservoirs on Trout Creek. Penticton Creek, there's Grayback Lake. Ellis Creek, there's the Ellis Lakes up at the top. Chute Lake is a reservoir for Chute Creek. And we have Narramana Lake and Big Meadow Lake up on Robinson Creek. So all of these are controlled flows in an attempt to store winter water for summer use. Just very quickly on the groundwater issue, basically there hasn't been any licensing on groundwater extraction, so we don't really have a good handle on the amount of water that we take out of the ground. But new legislation that is being introduced will presumably apply a new licensing structure, and the people who are involved in water licensing know more about this than I do, but this will be a big change for us in trying to understand our supplies and our demands. As I mentioned, the upland, the most groundwater flows into nearby streams. It goes into the rock, but very quickly exits as base flow in these upland creeks. A little bit flows all the way through the bedrock to the lake. And but when these streams exit the mountain system and come out into the valley floor, they go from essentially a bedrock lined stream bed out into an unconsolidated materials. At that point, much of that water can then leave the stream, enter into the unconsolidated sediments, and it feeds the local aquifers that then people pump groundwater from. So even though they're pumping groundwater, the origin of that water may have been as stream flow at higher elevation. All right, the last component here then is the natural hazards and their link to the hydrologic cycle. And I'm going to talk a little bit more about future climate scenarios, the change in the flow regimes that are projected as a result of our changing climate here.